One block sits 3 rows up in Sacsayhuamán's northern terrace, its face angled 15 degrees off vertical, wrapped by a seam that traces 3 separate surfaces without breaking rhythm. The joint gap measures under 1 millimeter, tighter than the expansion joints in modern concrete construction. The block itself weighs somewhere between 80 and 120 tons, roughly equivalent to 25 fully loaded dump trucks fused into a single piece of andesite. No mortar, no filler, just stone meeting stone with tolerances that should not exist outside factory conditions. The official story sounds reasonable: stone tools, abrasion paste, patience, and skilled labor over decades. But here's the problem that explanation cannot solve. The precision is not isolated to this one showpiece block. It is consistent across hundreds of joints, spanning multiple walls, multiple sites, and multiple construction phases. If this seam cannot be explained by bronze chisels and sand, the entire narrative about Inca construction capability starts coming apart at those invisible joints. Stand at the base of the zigzag wall and tilt your head back. The lowest course rises 2 meters, the one above it stretches 3 meters, and the blocks don't stack, they interlock, each face angled at a different pitch, each seam tracing a path that defies any attempt at pattern recognition. Earthquakes hit this region every few decades. Cusco shook hard in 1650 and again in 1950. Colonial buildings crumbled both times. The Sacsayhuamán walls moved. Witnesses reported blocks shifting slightly, then settling back, but nothing fell. The official record attributes construction to Pachacuti's reign in the 15th century as part of a defensive terrace system protecting the Inca capital. The design, archaeologists explain, emerged from empirical trial and error. Builders tested configurations until they found one that worked. But here's where the engineering constraint appears. Trial and error with 100-ton blocks is not iterative refinement. It is catastrophic when you guess wrong. The walls show no evidence of failures, no abandoned sections, no practice runs with smaller stones. The geometry appears fully formed, as if someone already knew exactly which angles would let seismic energy dissipate through controlled micro movements instead of accumulating into structural collapse. This raises an uncomfortable question. How do you design for earthquakes you have no written record of experiencing? Most ancient walls rely on simple compression, weight stacked on weight, keystones locking arches, gravity doing all the work through predictable load paths. Sacsayhuamán does not use that language. Each block contacts its neighbors at dozens of points, convex surfaces meeting concave pockets, projections slotting into recesses, faces that curve in 3 dimensions simultaneously. No arches, no keystones, just distributed load bearing across surfaces shaped like 3-dimensional puzzles. The official explanation frames this as patient empiricism, masons gradually refining techniques, learning through accumulated experience. But scale this to reality. You are working with stones that weigh more than a loaded cement truck. A single miscalculation means a block that will not seat properly, cannot be adjusted once lowered, and cannot be quietly discarded. The error rate has to approach 0 before you start moving the real pieces. Modern load path modeling software can analyze how forces distribute through irregular geometries. When engineers run simulations on Sacsayhuamán's joint patterns, the stress distribution is remarkably efficient. No concentration points, no weak zones where cracks would propagate. The geometry is not just functional, it is optimized. And optimization implies either mathematical planning or an error rate so low it suggests advanced knowledge of the final form. Trial and error does not scale to 100-ton stones, but something did. Run your hand across one of the finished faces. The surface is matte flat, absorbing light rather than reflecting it, with flatness deviations measuring under 2 millimeters across multiple meters. Edges meet faces in crisp transitions. Corners, where 3 planes converge at complex angles, show no rounding, no wobble, no compromise in precision. This is the finished texture, the final surface after all shaping is complete. The accepted toolset is bronze chisels, hammerstones, and abrasive sand paste worked across the surface with smaller stones. Experimental archaeology has replicated the basic technique. Yes, you can wear down andesite with these methods, but volume calculations become a problem. 1 cubic meter of andesite weighs about 2,600 kilograms. A typical block face might require removing several hundred kilograms of material to achieve final form. Abrasion is slow, hammerstones wear out, bronze chisels deform against crystalline rock. Researchers have attempted to model the time requirements. Estimates for finishing a single block stretch from months to years, depending on assumptions about crew size, work hours, and tool replacement rates. Multiply that by hundreds of blocks, stack it against rain timelines derived from historical records, and the calendar starts to stretch uncomfortably. Either the construction period was longer than Spanish chronicles suggest, or the process was faster than Bronze Age tools should allow. The math does not reconcile cleanly with either the timeline or the toolkit, and that is where it gets worse. The andesite quarries sit 5 kilometers away at Huacoto, across terrain that climbs and drops in sharp gradients. The blocks weigh between 80 and 120 tons. The official transport method invokes wooden rollers, fiber ropes, sledges, and large labor crews, essentially scaling up techniques proven effective for smaller stones at other sites. Here is the physics problem. A 100-ton block on rollers exerts ground pressure that exceeds the bearing capacity of most natural soils. Clay and silt compress under this kind of loading. You need either bedrock pathways or compacted road surfaces capable of handling concentrated stress. Surveys of the terrain between Huacoto and Sacsayhuamán show no evidence of prepared roadbeds with that load capacity. Then there is the gradient issue. Moving mass uphill on rollers requires overcoming both friction and gravity. As slope increases, the force needed scales exponentially. Beyond about 8 degrees of incline, the numbers stop working with human muscle and fiber rope. Several sections of the route climb steeper than that. Logistics simulations that plug in realistic friction coefficients, rope strengths, and crew coordination factors consistently show failure modes. Either the ropes snap, the rollers jam, or the load stalls on inclines. No one disputes the blocks came from those quarries. Chemical analysis confirms the match, but replicating the transport with claimed methods has never succeeded at this scale. Moving the stone turns out to be harder than cutting it, and we have not even tried to turn a corner yet. Watch the route on a map. The final approach to Sacsayhuamán narrows through sections where streets and ramps are less than 4 meters wide. Now visualize maneuvering a block that is 3 meters across in any dimension. On rollers, you need clearance on all sides. To turn, the block has to rotate around a pivot point, which means the outer edge traces an arc wider than the block's own dimensions. Basic geometry, a 3-meter block turning 90 degrees on a 4-meter path needs at least 4.2 meters of swept radius. The space isn't there. The official record stays silent on this detail. Spanish chroniclers describe the walls with awe but never explain transport logistics. Inca oral tradition, recorded generations after the fact, speaks of massive labor mobilizations, thousands of workers pulling ropes in coordinated effort. But coordination does not change turning radius. Physics does not negotiate. Some researchers propose the blocks were shaped smaller during transport, then finished on site to their final interlocking forms. That would solve the turning problem, but creates a new one. It means you are doing the precision fitting work in situ, without the ability to test fit pieces before final placement. Error tolerance drops even further, and there is no archaeological evidence of massive on-site finishing debris at the scale this explanation would require. The stone chips and dust from final shaping are not there in the volumes you would expect. So either the transport route was different, wider, more gradual, now erased by centuries of overbuilding, or the blocks arrived already shaped, and the turning problem was somehow solved by a method we have not identified. Neither option fits comfortably with the standard narrative. There is nowhere to turn, but the blocks arrived anyway. Get close to the finished surfaces under raking light. Standard hammerstone percussion leaves, characteristic marks, overlapping circular depressions where the stone impacts, radiating micro crack patterns, and surface roughness at specific scales. Experimental archaeology has documented what Bronze Age stoneworking looks like up close. there is a signature. Sacsayhuamán's finished faces do not show that signature. The surfaces are smooth, at scales where pecking marks should be visible. High-resolution photogrammetry scans reveal microstriations, but they are inconsistent with the angles hammerstone impacts would create. The patterns suggest controlled material removal across broad areas simultaneously, not point impact percussion. The official response points to final polishing phases, abrasion with progressively finer grit worked until all previous tool marks are erased. Experimentally, this process is possible. It is also extremely time-consuming and creates its own signature: surface waviness at millimeter scales, uneven removal around harder crystalline inclusions, and slight rounding at edges where hand pressure varies. Walk through Cusco and pay attention. Polygonal masonry appears not just at Sacsayhuamán but at Coricancha, at Hanan Cusco, and at retaining walls threading through the city's foundations. The joint logic repeats: irregular shapes, multi-point contacts, seismic fit geometry. Angles recur within narrow ranges. Face-pitch ratios cluster around common values. Construction signature consistency appears across multiple sites, built according to chronicles by different crews during overlapping time periods. The official interpretation treats this as phased construction within the Inca period. Early rough work establishes the foundations, and later master builders raise the monumental terraces. It is a reasonable reading, except for one uncomfortable detail. If we are watching the same culture develop techniques over time, we should see gradual improvement. Skill curves rise incrementally. You get slightly better precision, somewhat larger blocks, and gradually refined methods. That is not what the archaeology shows. The transition is abrupt. Foundation work is merely competent, and then suddenly, at a distinct layer, work appears that exceeds anything else in the region. No intermediate steps are visible. No practice runs show up in the stratigraphy. Now look at later Inca construction, the work clearly attributable to the historical empire's final decades. It is good masonry with regular courses and carefully fitted stones, but it does not match the precision of the lower terraces. The stones are smaller, the joints are tighter than typical ancient work, but they are nowhere near Sacsayhuamán's tolerances. If we map the progression chronologically, it shows a peak followed by a decline. This brings us to the real problem. Why would builders get worse over time? Skills once learned tend to persist or incrementally improve. They do not suddenly vanish within the same cultural continuum. Either the foundation to terrace transition represents a longer time span than current dating allows, or the peak precision work was not the latest achievement, but something inherited or rediscovered. Neither option fits neatly into the 15th century Inca timeline. The stone layers tell a sequence that does not match the historical one. Spanish conquistadors arrived in Cusco in 1533 and immediately began appropriating Inca structures as foundations for colonial buildings. They were not subtle about it. Catholic churches rose directly atop Inca temples. Spanish mansions anchored themselves to existing platforms, and administrative buildings reused perfectly good walls because, candidly, the Spanish could not replicate them. 16th century chroniclers are explicit about this. Pedro Sancho wrote that the stones were so close together and so well fitted that they seem to have grown naturally that way. Garcilaso de la Vega, himself part Inca nobility, described later Inca attempts to replicate ancestral techniques and noted they achieved good results but could not match the precision of older work. He is describing cultural memory of capability decline, not advancement. The Church of Santo Domingo in Cusco sits directly atop Coricancha's Inca foundations. Tourist guides point out the beautiful polygonal masonry at ground level, then the cruder Spanish stonework rising above it. The contrast is visceral. Colonial builders with steel tools and European masonry traditions reused what they could not rebuild. That is not architectural laziness. It is a practical admission that the techniques were not readily accessible to them, even though they theoretically had better tools. Modern replication attempts have not fared better. Stone sculptors with diamond-tipped tools, tungsten carbide bits, and electric power can achieve similar surface finishes. The time required still balloons, and producing truly invisible joints at this scale remains elusive. Computer-controlled cutting could do it, obviously. That is not the point. The question is simpler. If Bronze Age techniques could achieve this, why cannot anyone demonstrate the full process convincingly, start to finish, at comparable scale? They reused what they could not rebuild, and several centuries later, we still cannot rebuild it either, which suggests the gap between claimed capability and demonstrated reality is wider than anyone wants to admit, which opens a different possibility. Maybe what we're seeing isn't a single construction phase, but a remodeling project. Older walls supplemented with new blocks, ancient platforms topped with fresh terraces, inherited foundations built upon by later dynasties. The Spanish chronicles describe Inca history in neat generational sequences, but oral tradition compressed into written narrative often loses resolution. Decades collapse into single reigns. Centuries blur into legendary, founding moments. The stones disagree with the date, and stone, unlike chronicles, doesn't negotiate with political narratives. Polygonal masonry with seismic-resistant joint patterns shows up in scattered locations worldwide, not everywhere, but enough places to make independent invention feel statistically strained. The Osirian in Egypt uses massive blocks with similar multi-point contact logic. Certain Cyclopean walls in Mediterranean sites show comparable joint patterns. Pre-Columbian construction in Peru obviously displays it extensively. The technique crosses continents, cultures, and supposed isolation. The mainstream position invokes convergent evolution, similar problems producing similar solutions. If you are building in earthquake zones with available stone and no mortar, irregular interlocking joints are a logical response. The physics are the same everywhere. Different cultures could independently arrive at the same engineering solution, except the details are almost too similar. The face angles cluster around the same ranges. The load distribution principles repeat. Even the construction sequence, with massive foundations and precision upper courses, shows up across geographically disconnected sites. Convergent evolution explains functional similarity. It does not easily explain nearly identical implementation details. This does not prove ancient global contact. It does not prove lost civilizations teaching the same methods everywhere. But it does pressure the independent invention narrative. Physics travels better than myths, yes. But engineering signatures this specific, that is harder to wave away as coincidence. The question is not whether people could figure this out independently. It is whether this level of technical overlap is statistically plausible across cultures that supposedly never interacted. Chroniclers describe Inca walls with admiration bordering on disbelief, but they never explain construction. The accounts read like tour guides, not engineering documentation. They note the size, marvel at the joints, mention thousands of workers, then move on. There is no parallel to Roman engineering texts detailing lifting machines, no equivalent to medieval masons' manuals specifying tool types and techniques. The records are suspiciously empty, where you would expect documentation, because state societies obsessively document logistics, especially for monumental projects. That is how states function. So here we are, back at that first impossible seam. The measurements are real. The joints measure under 1 millimeter. The blocks weigh over 80 tons. They have survived 5 centuries of earthquakes that collapsed Spanish cathedrals. The official story lists bronze tools, patience, and skilled labor, and it sounds reasonable until you stack all constraints simultaneously: transport logistics, precision finishing, timeline compression, weathering inconsistencies, replication failure. Any one contradiction might be explainable. Taken all together, the stones work better than we can explain, which means the real mystery is not what they built. It is what we refuse to see.